So today we're going to continue our discussion of the transient analysis of first order circuits. And what we're going to be looking at are the forced and total responses of first order circuits today. But before we get into that, I want to talk about kind of a subtopic that is related to not only the forced and total responses, but also the natural response. Okay. So, essentially, in our class meeting on Monday, we looked at RL circuits in general. So something akin to this. And what we derived for our inductor current and everything in general, based on an extension of what the inductor current is doing, is that our natural response was of the form y sub n as a function of time would have been equal to y at 0 minus for t less than or equal to 0 minus and y at 0 plus e to the negative req over leq multiplied by time for t greater than or equal to 0 plus. Okay. And we also looked at RC circuits. So something akin to this. So here's our REQ. Here is our CEQ. And this is the voltage drop across our capacitor as a function of time. And because our capacitor voltage was derived to have an exponential decay, we found that our natural response for these systems looked generally like this, where we would have, once again, y at 0 minus for t less than or equal to 0 minus, and then y at 0 plus, e to the negative t divided by req times ceq for t greater than or equal to 0 plus. And so it's not hard to see how extraordinarily similar these equations are to each other, right? So if we have an RL circuit, really the only difference is that we use REQ and LEQ to determine the rate at which our exponential function is decaying. And when we have an RC circuit, we use REQ and CEQ to determine the rate at which our exponential function is decaying. So because these guys are so incredibly similar to each other, electrical engineers have decided to express that rate of exponential decay as a generic term, which is what's called a time constant for our circuit, okay? So a time constant for our circuit is very similar to the half-life that you probably heard about in chemistry. It's just defining that rate of exponential decay. So in electrical engineering, we define one time constant. Let me write this down. So a time constant tau, that is a shitty looking tau, is defined as the amount of time it takes for a signal to decay to a factor of e to the minus 1 of its original value. So essentially what we can do is we can make a table with this definition, okay? So let's say that on this left-hand column for this table, I'm going to put the amount of time that has elapsed. And on the right-hand column of this table, I'm going to put y of t divided by y at 0 plus. So this is simply a ratio of whatever value the time, the signal y of t has compared to its initial value, okay? So at one time constant, this is going to be simply e to the minus 1. And if I put e to the minus 1 in my calculator, this turns out to be 36.788%. Okay. So effectively in one time constant, our signal decays down to a little less than 37% of its initial value. Well, in two time constants, that's going to look like e to the minus 2, which is 13.534%. Going on, in three time constants, our ratio would be e to the minus 3, and that is 4.979%. In four time constants, that's simply e to the minus 4, or 1.832%. And the last one that I'm going to put here is five time constants, or e to the minus 5. And this is 0.674%. So it takes only 5 time constants for our signal to decay from its maximum initial value down to less than 1% of its initial value. So this is what we have collectively agreed to represent t is equal to infinity, okay? So if we allow a signal to decay for 5 time constants or more, we consider that it has reached DC steady state again, okay? So as far as we are concerned in this class, 5 tau is simply the length of infinity, and that's going to change for every given circuit, depending on what values of resistance, inductance, and capacitance that circuit has. So this essentially tells us how long we need to allow this circuit to either discharge, or as we'll find out in a couple of moments, charge in order to hit some steady state value. Okay. So based on this definition that I have up here, where a time constant is defined as the amount of time it takes for the signal to reach a value of e to the minus 1, we can simply figure out what value of t causes that to happen for RL circuits and RC circuits, right? So for an RL circuit, our time constant tau is simply going to be LEQ divided by REQ. Because if I plug in tau for the value of t there, then I have REQ times LEQ over LEQ times REQ, or just 1, right? And pretty similarly, we can see that for an RC circuit, our time constant tau is just going to be REQ, goodness, that Q looks terrible, multiplied by CEQ. So from today onward, anytime we're analyzing any of these transient analysis problems, I'm going to modify our fourth step, right? So step one, as we discussed on Monday, was to analyze the circuit at t is equal to 0 minus. That's going to stay completely the same. Step two was to analyze the circuit at t is equal to 0 plus. Once again, that stays completely the same. Step three was analyzing the circuit at t is equal to infinity. What we're dealing with today, that is no longer going to be just everything is 0. So this is going to be an important part of our process. Step four was calculate LEQ and CEQ, or excuse me, LEQ and REQ, or CEQ and REQ. I'm now going to call step four, calculate the time constant for the system, which inherently requires us to calculate REQ and CEQ as well. Okay. And then step five is once again just going to be plug everything in. Okay, so before we move on from this concept of time constants, does anybody have any questions about what it is, how to calculate it, what it means? All right. So now we're going to talk about our forced and total response, okay? So I'm going to define the total response of a circuit as this generic quantity Y total. And it is simply going to be the sum of our natural response, which is what we dealt with on Monday, and what I'm going to call our forced response, which is what I'm going to call Y sub F as a function of time, okay? N. So I'm going to make a little note here. This is the natural response. Y sub F is the forced response. And Y sub total is the total response. Okay. So I want us to look at a simple example to get an understanding of what the forced response means. Okay. So I'm going to look at an RC circuit. Okay. Very similar to the one that we looked at roughly halfway through class on Monday. Okay. So here I've got my simple DC voltage source, VS. Here's my switch. Here's my resistance REQ. Here's my capacitance CEQ. And this is my voltage VC as a function of time, okay? So in all of the examples that we worked on Monday, our switch operated in such a way as to take our source out of the system, okay? Well, today we're going to be talking about what happens when our switch works to leave a source connected, okay? So our forced response is nothing more than effectively the effect of our forcing function. In this case, it's just that voltage source Vs on the capacitor voltage that we're interested in, okay? So essentially, the presence of that voltage source Vs is going to force the voltage drop across the capacitor to approach Vs as time increases. Okay, so that's all the forced response is. So we can essentially just say that our forced response is really just y at infinity, or what our signal settles to after we wait a long time for the transient to decay. Okay, and that will only be non-zero when there are sources present in our system that are making it not zero. Okay. So if we use this simple definition for our total response, then we might find, and for what it's worth, there is going to be a little bit of an error in here that we're going to fix, so you might not want to write things down just yet. But we might find that our total response, actually, let me do this as VC, right? So our total response for our capacitor voltage might look something like this. So we'd have our capacitor voltage at 0 minus for t less than or equal to 0 minus. And then just using this simple mathematical function, we would have our capacitor voltage at 0 plus e to the minus t divided by tau, where I'm putting that REQ times CEQ and expressing it as my time constant, plus VC at infinity for t greater than or equal to 0 plus. But there is a little problem here. Can anybody tell me what that is? So if I evaluate that expression on bottom, for t is equal to 0, what do I get? VC at 0 plus times e to the 0, which is just 1, plus VC at infinity. So for this particular circuit, what would VC at 0 minus be? So we start off with our voltage source disconnected. So if we have a capacitor connected to nothing, no sources, what would we expect the voltage drop across our capacitor to be? 0, right? So VC at 0 minus should be 0. Okay. What then is VC at 0 plus supposed to be? 0. Because the voltage drop across the capacitor cannot change abruptly. So whatever value it had at 0 minus, it has to continue having at 0 plus. What is VC at infinity going to be? Vs. So we would have a capacitor in parallel with the resistor in parallel with the voltage source. So eventually the voltage drop across the capacitor is going to charge all the way up to Vs. So if I evaluate this bottom expression at t is equal to 0, I wind up getting 0 plus Vs. Well, 0 plus Vs is not equal to the value that we had at 0 minus. So our capacitor voltage appears like it is it has a discontinuity in it. So in order to fix that, what I'm going to do is I'm going to mess with that initial condition term a little bit here. Okay, so I'm going to erase this guy. And I'm going to replace it with y at 0, or excuse me, VC at 0 plus, sorry, minus VC at infinity, close that off, e to the minus t over tau, plus VC at infinity. And this correction effectively makes this whole term right here look like negative Vs, so that when I add these two bits together at t is equal to 0 plus, I have 0 volts for 0 minus and 0 volts for 0 plus, forcing this to be a continuous function of time. Okay. So this is essentially our new generic equation, okay? We're always going to have to make that correction. So we are going to have y total as a function of time will be equal to y at 0 minus for t less than or equal to 0 minus, and then y at 0 plus minus y at infinity, e to the minus t over tau, plus y at infinity for t greater than or equal to 0 plus. That is the new generic equation that we are going to use in step 5. Okay. Now, we're going to work some examples here, and I'm going to try very hard to explain what the difference between a natural response problem and a total response problem is. But despite my best efforts, some of you are just not going to catch what I'm throwing. It will be perfectly okay because you can realistically just use this generic equation for the total response for literally everything and be perfectly okay, because what you'll find is that if it's actually a natural response problem, y at infinity is just going to go to 0, and this simplifies down to exactly what we did on Monday. So worst case scenario, you waste 20 to 30 seconds analyzing the circuit at t is equal to infinity and go, oh yeah, everything is 0. I didn't need to do this, and then go on about your day. Carter. Uh, I don't know what you mean by off to on. I have it going from open to closed.
On four sides, y at infinity.
Yes.
It's always closed.
Yes.
And that time charge up. So does that work the same when it goes from closed to open?
So when we go from closed to open, we don't have a forcing function in our system, which is why it's always settling to 0. So effectively, our forced response is 0, which means we didn't need to bother including it. So that's literally what I was getting at right here, right? So if we look at this expression right here, and we can't tell the difference between whether this is a natural response problem where all of our sources have been switched out of the system, or a total response problem where some of our sources are left in the system, if we treat it as a total response problem, regardless of what it is, we'll always get the right answer because our forced response is 0 in a natural response problem. So that y at infinity term is just going to be, so y at 0 plus minus 0, e to the negative t over tau plus 0. It is literally the exact same result that we got on Wednesday or Monday. So you technically can't go wrong if you just treat everything as a total response problem. You're just wasting a little bit of time proving that things go to 0 because you couldn't correctly identify the type of system that you had. Okay. So yes, Teresa.
I also did have this LQ RQ, but for RC, it's RQ to CQ. How do you plug that in? Can you the overtime? And how do you plug in for an RC circuit? Is always that.
So tau is the amount of time. So that is what's being substituted for t. Correct. So tau is a constant that you calculate, and then t is the time that you're interested in. So if let me work an example and I'll find something specific and we'll show how that works out, okay? So let's say this will be similar to some of your homework problems and stuff like that, okay? So let's say that we have the following circuit. Here I've got a 20-volt source in series with a 5 ohm resistor. And then I've got a switch here, and this switch is going to be closing at t is equal to 0. Here's a 20 ohm resistor. A 5 ohm resistor. An 18 ohm resistor. A 2 Henry inductor. I'm going to define my inductor current IL of t in this direction. And then across the top, I'm going to have another current source. 18. Oh, so the one on the left is 20. And for what it's worth, let's define this voltage as VR of t, okay? So this is our system. So the first thing that I would typically want to do is look at this and determine if it is a total response problem or a natural response problem, okay? So I can look at this and see that this is a total response problem because regardless of what my switch is doing, that 2 amp source is still connected and will influence the behavior of the inductor at t is equal to infinity. So even if that switch opened, removing that 20-volt source, it would still be a total response problem because nothing ever turns that 2 amp source off, okay? So anytime that we are going to have a source left in our system at t is equal to infinity, it's a total response problem. That's the difference. Total response has sources left in, natural response has sources switched out. Okay. So this is a total response problem, okay? So our process for this is going to be pretty much exactly what we did on Monday. We're going to analyze this system at t is equal to 0 minus. Okay. So let's just write that step down. So at t is equal to 0 minus, our switch was opened. So our circuit would look something like this. So there's our 20-volt source. Here's our 5 ohm resistor. Here is the open circuit representing the switch. Here's our 20 ohm resistor, our second 5 ohm resistor, an 18 ohm resistor. Because we're at 0 minus, this is DC steady state, so our inductor is going to look like a short circuit. Here is our current source over the top of our system. And ultimately, we are trying to find this voltage, VR of t, and this current IL, sorry, that VR should be at 0 minus. So how might we analyze this circuit to find either of those two quantities? Mr. Maestri. So the 20-volt source and the 5 ohm resistor are literally going to do nothing. Absolutely. So we can literally just X those guys out. They're not going to have any influence on anything because they're not, that path isn't closed. We can do current division. So just to make sure everybody sees why we can do current division, I'm going to identify our nodes here. Okay. So I've got this node right here. And then I've got this node down here. So I hope everybody remembers that whenever an element is touching the same node on both sides, like the 18 ohm resistor here, it is shorted out and we could ignore it. So essentially what we have is a 2 amp current source in parallel with a 5 ohm resistor in parallel with the 20 ohm resistor. So the 5 is between 5 current source and 20 is all shared between green and blue, okay? So that current IL at 0 minus, as we follow it along, is essentially going to be this current flowing up through that 20 ohm resistor, right? We know that none of it's going to flow up through the 18 ohm resistor because it's shorted out. We know that none of it can continue on to the left and flow through that voltage source because that branch contains an open circuit. So its only path is up through that 20 ohm resistor. So we can find IL using current division. Now notice that IL is flowing into the green node and the 2 amps is also flowing into the green node. So what we should find using current division is that IL at 0 minus is going to be negative 2 amps times 1 over 20 divided by 1 over 5 plus 1 over 20. I'm going to throw that into my calculator real quick. Damn it. And I got negative 2/5 of an amp. So before we move on from here, does anybody have any questions, comments, or concerns about how I calculated that? All right, so how might we calculate VR at 0 minus? What was that? So we could, so the voltage drop across the 20 ohm resistor is going to be the same thing as the voltage drop across the 5 ohm resistor. We need to pay attention to polarities. I would argue, and I mean, this is essentially the same thing. Our 2 amps times 5 in parallel with 20 is going to give us the same result. So that's probably what I would do. Zach. Sorry, what? It's utter overkill because there are only 2 nodes. One of them is ground. Right. But what I'm saying is you're setting up an equation when we could just use Ohm's law. So why not just use Ohm's law? So VR at 0 minus, notice that the 2 amps is flowing into the positive polarity terminal, is going to look like 2 amps times 5 ohms times 20 ohms over 5 ohms plus 20 ohms. So I believe that's 100 over 25 is 4. So I think this is going to come out to be 8 volts, but I'm just going to double check because I don't trust my ability to do math without having had a crap ton of coffee. It is indeed 8 volts. All right, so any questions, comments, or concerns about the analysis that we did here at 0 minus? Okay. So step 2, we're going to analyze our circuit at 0 plus. So at t is equal to 0 plus, our switch is now closed. So our circuit should look something like this. So here's my 20-volt source, 5-ohm resistor, 20-ohm resistor, 5-ohm resistor, 18-ohm resistor, 2-amp current source. What do I replace my inductor with at t is equal to 0 plus? So what do we know about our inductor current? It cannot change between 0 minus and 0 plus. So whatever current we had flowing through that branch at 0 minus, we have to have flowing through that branch at 0 plus. So I choose to represent that with a current source, where the current source has the same magnitude and direction as IL at 0 minus. So IL at 0 minus was defined down, so my current source is pointing down. Its value is determined to be negative 2/5 of an amp, so I'm going to give it a value of negative 2/5 of an amp. And the only thing that we actually need to solve for is then this voltage VR at 0 plus, and I'll write this down to make it hopefully stick. IL at 0 plus must be IL at 0 minus, which is negative 2/5 of an amp. So how might we go about solving for VR at 0 plus? Which analysis? Nodal. Okay, so we could do nodal. So let me just look here really quickly. So if we do nodal analysis, this guy is known, so that's just 20 volts. This is one node I don't know. This is another node I don't know. And then I would choose the bottom as the ground. So that would be a 2-equation, 2 unknown system. So that would be pretty simple. If I did mesh analysis, which I think some of you are probably looking at, I would have 4 meshes, but I have 2 perimeter current sources, which means that effectively 2 of those mesh currents are also known quantities. So it's going to be a 2-equation, 2 unknown system, whichever way we slice it. Let's do nodal. So I'm going to call this voltage V1, this voltage V2, and put my ground down here. So KVL at V1, or excuse me, KCL at V1 is going to look like V1 minus 20 volts over 5 ohms plus V1 over 20 ohms plus V1 minus V2 over 5 ohms minus 2 amps is equal to 0. KCL at node 2 is going to look like V2 minus V1 over 5 ohms plus 2 amps plus V2 over 18 ohms plus negative 2/5 of an amp is equal to 0. And I'm just going to solve that system. Yep. Yeah. Just to be clear, because if you were asking a question about it, somebody else might have missed it. So the arrow for this current source is down because IL at 0 minus was defined to be down. Right, so it has to have the same magnitude and direction from 0 minus to 0 plus. All right, so solving this system. So we've got a 2x2 system. My coefficient for V1 in my first equation is 1/5 plus 1/20 plus another 1/5. My coefficient for V2 is -1/5. And my constant term is going to be 20/5 plus 2. In my second equation, my coefficient for V1 is -1/5. My coefficient for V2 is 1/5 plus 1/18. And then my constant term is going to be -2 plus 2/5. So when I solve this system, I got V1 to be 728/45 volts and V2 to be 32/5 volts. Did anybody else solve that system and get similar results? So, assuming I'm correct, the process was right even if I typed it into my calculator wrong. How would we determine VR at 0 plus from these nodal voltages? V1 minus V2. Which I get to be 88/9. All right, so anybody have any questions about what we did here for step 2? Yes, ma'am. So the 20 volts over 5 ohms is a constant that just gets moved to the other side. So that was 20/5 plus 2. I'm sorry, I couldn't hear you. Mm-hmm. No, so if we take the difference of the voltages and divide it by 5, that's giving us a current. V over R is I. The difference of the voltages is the voltage that we're looking for. Any other questions? All right, so let's look at step number 3. So now we are going to analyze the circuit at t is equal to infinity, okay? So it is technically possible for us to get answers of 0 here, but we might get non-zero results, which is why we have to do this, okay? So at t is equal to infinity, we're at DC steady state. So my switch is closed, but my inductor is going to look like a short, okay? So incorporating that information, our circuit's going to look something like this. Here's our 20-volt source. Here is our 5 ohm resistor. $20 ohm resistor. Second 5 ohm resistor, across which we're trying to find VR at infinity. An 18 ohm resistor. My inductor, as I mentioned, is replaced by a short circuit at t is equal to infinity because we are now at DC steady state because the transient condition is over. And then across the top up here, I have that 2 amp current source. And this is the IL at infinity that I'm trying to find. Okay. So one thing that I want to point out, and we saw this earlier, that 18 ohm resistor is in parallel with our inductor. And because our inductor is behaving like a short circuit, that means that this 18 ohm resistor can essentially be neglected. Okay. So any thoughts on how we might solve this system? So at t is equal to infinity, we have reached DC steady state again. So we are analyzing a DC circuit. Inductors look like short circuits in DC circuits. So just to be really, really clear about this, we talked about it on Monday. T is equal to 0 minus is DC steady state. T is equal to infinity is also DC steady state. It's that space in between that is the transient condition where things are changing and we can't strictly do DC circuit analysis. That's why we had to develop that differential equation, solve it, et cetera, et cetera. So how are we going to solve this circuit for IL or VR? Mesh. Sure, why the hell not? So let's say that this is mesh current I1. This is mesh current I2. Or I'm choosing to lump those two boxes together because I know that no current is going to flow through that 18 ohm resistor. So it's effectively behaving like an open circuit. And this guy up here will be I3. Okay. So we can say that 2 amps is equal to negative I3. So there's our current source relationship. Then we're going to apply KVL around mesh 1. So that's going to look like negative 20 volts plus 5 ohms times I1 plus 20 ohms times I1 minus I2 is equal to 0. And then lastly, we're going to have 20 ohms times I2 minus I1 plus 5 ohms times I2 minus I3 is equal to 0. So before I throw this into my calculator, I want you guys to double check and see if I made any mistakes. I don't think I did, but it's early. If anybody has any questions about anything, please let me know. So since nobody's saying anything, I will assume these equations are correct. And so now I'm just going to throw them into my system solver on my calculator. So in my first equation, my coefficient for I1 is 0. My coefficient for I2 is 0. My coefficient for I3 is -1. And my constant term is 2 amps. In my second equation, my coefficient for I1 is 5 plus 20. My coefficient for I2 is -20. My coefficient for I3 is 0. And my constant term is +20. In my third equation, my coefficient for I1 is -20. My coefficient for I2 is 20 plus 5. My coefficient for I3 is -5. And my constant term is 0. And when I solve this system, I get I1 is equal to 4/3 of an amp. I2 is equal to 2/3 of an amp. And I3 is equal to -2 amps. So using that mesh analysis, what is IL at infinity going to be? I2, which is just 2/3 of an amp. What's VR going to be? 5 ohms times I2 minus I3. So putting that into my calculator, that's 5 times Y minus Z. And I get 40/3 of a volt. Does anybody have any questions about our analysis for step 3? All right, so let's move on to step 4. So for step 4, we are simply trying to determine how during the transient condition. Okay. So, silly question. I hope it's a silly question, or not necessarily a silly question, but an easy question. Is this an RL circuit or an RC circuit? It's an RL circuit because there's an inductor, there aren't any capacitors, right? So because this is an RL circuit, tau is going to be equal to LEQ, times REQ. No, that's totally wrong. LEQ over REQ. Well, I believe that our equivalent inductance is simply 2 henries because it's the only inductor in our circuit. Let me just scroll up here to double check that we have the right value. That is indeed a 2 Henry inductor. So I think we're all pretty okay with saying that LEQ is 2 henries. To find R, we need to find the equivalent resistance or the Thevenin resistance as seen by that inductor during the transient condition, okay? So I'm going to draw my circuit during the transient. So here's my 20-volt source. Here's my 5 ohm resistor, 20 ohm resistor, 5 ohm resistor, 18 ohm resistor, inductor, two amp source across the top like so. Okay. So I'm finding the Thevenin equivalent resistance with respect to my inductance. So I take my inductor out, leaving behind a set of terminals, and I'm going to look in here. Because I'm finding the Thevenin equivalent resistance, I need to be looking at a dead network, which means I need to turn this 2 amp current source off. So it's replaced with an open circuit, and I need to turn this 20-volt source off. So it's replaced with a short circuit. So what do we see? So 20 is in parallel with 5. How is that connected to the middle 5 ohm resistor? In series. And then that whole thing is just in parallel with the 18 ohm resistor, right? So 20 times 5 over 20 plus 5, I believe, is 4. So we have 9 in parallel with 18, which I think is 6, but I'll double check. Yeah. If anybody wants to throw that in their calculator to verify, by all means do so. So for what it's worth, and I believe I mentioned this on Monday, Surprisingly enough, calculating the equivalent resistance is one of the places where I see students make the most mistakes. Okay? So I want to be very, very clear about this process. When you're calculating REQ to determine your time constant, you are finding a Thevenin equivalent resistance with respect to your energy storage element. So an inductor in an RL circuit and a capacitor in an RC circuit, okay? So you would take the energy storage element out, turn off all of your independent sources, and then it's just a simple resistor combination problem looking into the terminals where your energy storage element was connected, which is exactly what I did here, right? I redrew my whole circuit, took my energy storage element out, indicated where I was looking in so I wouldn't get confused because there's multiple open circuits here, and then turned off all of my independent sources. And then I calculated REQ. So putting these two pieces of information together, we have 2 Henrys divided by 6 ohms is going to look like 1/3 of a second. And for reasons that will become very obvious in a moment, the inverse of tau is then simply 3 per second. So now, unless anybody has any questions, we're ready for step 5. Yes, ma'am. It will make more sense here in step 5. Because it's an RL circuit. So for all RL circuits, tau is equal to LEQ over REQ. Yes, so it just is because, so if we evaluate things, let me scroll way back up to the beginning, right? So we defined a time constant as the amount of time it takes for a signal to decay to a factor of e to the -1 of its original value, right? So if I have a basic RL circuit where I have something e to the minus REQ over LEQ, if I substitute in a value for time that is LEQ over REQ, this becomes e to the -1. This thing right here, then by definition, has to be tau because it makes that e go to just -1. Okay, so plugging stuff in. Unless anybody has any more questions. Okay. All right. So as a reminder, here is our generic equation, right? So our total response is going to be y at 0 minus for t less than or equal to 0 minus. And then we'll have y at 0 plus minus y at infinity, e to the minus t over tau plus y at infinity for t greater than or equal to 0 plus. Now, the reason why I choose to find tau to the -1 is because this guy right here, let me use it in a color that you can actually see, could also be expressed as e to the -t times tau to the -1. So when I flip that guy over, in this case, it's just going to look like e to the -3t, because that's easier for me to write than t divided by 1/3 kind of thing. So that's just my personal preference. Mathematically, it's all going to come out in the wash. But I prefer to express e to the -t over tau as e to the -t times the inverse of tau so that it looks prettier. That's literally the entire reason I do it. Okay. So using this relationship, let's figure out what's going on with our inductor current first. Okay. So what was the value for our inductor current at t is equal to 0 minus? Negative 2/5 of an amp, right? And then because we're dealing with an inductor current, it can't change abruptly. So it was also negative 2/5 of an amp at 0 plus. What was the value of our inductor current at infinity? Two-thirds, positive 2/3, right? Close that off. E to the negative t times the inverse of tau, which was 3 per second, plus y at infinity is going to be another 2/3 of an amp right here for t greater than or equal to 0 plus. And then what I'm going to do out here on the right is literally just pretty this up a little bit, okay? So the negative 2/5 of an amp can't get any more simplified than that. Negative 2/5 minus 2/3, according to my calculator, is negative 16 over 15. And there we go. Where, just to make it incredibly obvious, or at least that's my goal, these two things that I've underlined in pink are supposed to be the same thing. So now let's figure out VR of t using the exact same process, right? So what was VR at 0 minus? 8 volts, thank you. What was VR at 0 plus? You guys are mumbling or I'm half deaf, one or the other. 88 over 9? What was VR at infinity? And then I'm going to have e to the minus 3t plus 40/3 of a volt for t greater than or equal to 0 plus. And then once again, I'm just going to pretty this up. So our resistor voltage is going to look like 8 volts for t less than or equal to 0 minus, let's see, 88 over 9 minus 120 over 9 is going to be negative 32 over 9, or I could just not be a jackass and put it in my calculator. Yep, minus 32 over 9. E to the minus 3t plus 40/3 of a volt for t greater than or equal to 0 plus. All right, so I would like for you guys to spend the next 43 minutes or so working on your in-class assignment. It's only 2 problems, so you might finish a little bit early. If anything as part of the process doesn't make sense, please, please, please let me know. In our class next Wednesday, so I'm not going to see you guys for a week because of the Easter holiday and all of that kind of stuff, we are going to work one example problem where we have multiple energy storage elements as opposed to multiple resistors and all of that kind of stuff, and sort that out, and then we're just gonna do our lab. As far as I'm concerned, we've actually finished all of the material. So technically speaking, this was our last real class meeting for material on exam number 2. So exam 2 is just Thevenin and Norton equivalent circuits, capacitors and inductors, and then transient analysis. That's all the material that's on exam 2.